for electrodes, right? And I'm sure you will enjoy his presentation today. Sam, the floor is yours.
Okay, thank you so much, Alejandro, for the invite. The talks so far have been absolutely fascinating, and I think this connecting part where you're trying to join together the actual manufacturing processes is so vital. And I think there's kind of a joke amongst the battery modeling community that so much of the modeling work, the optimization work, we have poured time into it. And part of the reason that it's a lovely piece of maths, it's a lovely maths problem. But ultimately, it isn't useful until you connect it to manufacturing. So I think, you know, the work going on here is absolutely vital, and it's been great to be a part of it today. So I am going to be talking to you about two particular papers today. One, as Alejandro alluded to, is about a machine learning approach to microstructural generation in silico. And the second one is a collaborative study with some other researchers from Picardy, led by Charles Delacour, and the piece of work is by his fantastic student too. And so I'll introduce that in the second half of the talk. And you can see my slides okay, I'm assuming. Yes, okay. Right. So for those of you who don't know, here is a picture of Imperial College London. And this is us nestled into the middle of a sunny day in London, not so much like today. We're a very dense campus, and we focus only on, we're sort of a technical institute, so we focus only on science and engineering and medicine. I am part of a consortium of academics, so there's 9 of us, and we all focus around electrochemical energy storage devices. And then through that 9 of us, we have a team of nearly 100 PhDs and postdocs, all doing fantastic work across a wide range of length scales, everything from a few people even on the atomistic side, all the way up to devices and techno-economic studies. And my particular area of interest tends to be around microstructural characterization as well as device level prediction. And in particular, recently, the UK has kicked off a very large pool of funding called the Faraday Institution, which is funding projects all across battery activities. So we're working on the modeling aspect in collaboration with many other UK institutions, but there are people working on solid state cells, degradation, recycling, many aspects to try and make sure that the UK is part of the next generation of the battery industry. So I think the case has been already made in quite a compelling way that actually there is a relationship between electrode microstructure and battery performance. I don't think I need to spend too much time dwelling on that after the great talks in the last few days, but there is no doubt about this. And in the last maybe 10 or less than 20 years, imaging techniques, whether that's with X-rays or ion beams, have enabled us to see the actual microstructure at the micro and nano scale. And this has allowed us to start probing that microstructural data to try and understand what this connection is. What is this relationship between performance and microstructure and geometry? So the first paper I'm going to talk about is from the fantastic Andrea Gayon Lombardo, who is a student of mine at Imperial, and she's recently published a paper, Pause for Thought, Generative Adversarial Networks for Stochastic Reconstruction of 3D Multi-Phase Electrode Microstructures with Periodic Boundaries. What does all of that mean? So before I dive into the details, I want to give a quick introduction to the machine learning methods that we have made use of in this study. So hopefully anyone, even those of you who have never touched code or machine learning, can still follow along. So here's a classic schematic diagram of a neural network. And if that expression itself is even mysterious to you, hopefully I can demystify it. It is just a function. It is a deterministic function. Some numbers come in one side, numbers come out the other side. The magic is in the training of that function. Okay, the magic is in the fact that if you can teach it to learn which particular parameters to have inside this large function in order to get the correct or the useful relationship between what comes in and what goes out. So here is a simplified representation of what that network diagram is showing you. Numbers go in, numbers come out. The particular machine learning paradigm that we've made use of is the generative adversarial network, which was only even invented 5 years ago. And it's about trying to make two neural networks battle each other, basically. So imagine you have a detective whose job it was to identify counterfeit currency, fake money, okay? And you train him up, goes to an academy and learns the skills of identifying fake money. And you've also got a criminal who is trying to generate fake examples of money. And what you do, you get to play God in this game. You get to keep giving them both little clues about what the other one is up to. You make them battle each other until they keep getting much, much better at the skill. And in reality, of course, these two are not people. They are both just neural networks. The particular configuration that we have made use of, I'll show you here. It starts with some training data, and you can use that training data to train the detective, what we call the discriminator network. And these are deep convolutional networks, which just means that they are particularly well suited for image analysis. Then you make your generator network, the criminal, the counterfeiter, and you make them play off each other with an algorithm that keeps updating their internal parameters in order to keep making the detective better at spotting the generator and the generator better at fooling the detective. And when you have completed that process, you have a machine, this generator, where you give it some random numbers and it will give you an example of microstructure. And that microstructure looks absolutely like the tomographic training data that you showed it initially. And you can do some rather interesting things with that, as I will show you later on. So which data did we use? We made use of two open source training sets, one from NREL up in the States, where they have imaged at a scale where they can resolve the active material, but they've added the CBD binder mix later on. And another data set, which is a FibSem based data set of a fuel cell anode microstructure. And we've used the same machine learning architecture in both cases. And we wanted to use that to show to our readers that they can, in fact, generate a diversity of microstructures, or perhaps even any microstructure. It's not about the architecture itself, but the training data that gives that difference. So to skip straight to the end, what does it look like? Well, here are 6 examples, little small examples of each training set. I'm giving you 2D slices, but actually all of this work is done in 3D, not 2D. And here's what generated instances look like. So I hope you can see from this little subvolumes that actually they are qualitatively very similar. But what I'd like to show to you is that they are also quantitatively very similar as well. So just to highlight the fact that, of course, there are many alternative methods for generating synthetic microstructure, perhaps the most famous and intuitively graspable of which is some of the dropped spheres methods. We've also seen some of these spherical type methods today. And of course, when you use spheres, you can do things much more computationally efficiently. But there are downsides to this. These simplifications may lead to simplifications in your understanding of what's really going on at the microscale. So how does our microstructure that we generated compare to the training data that we obtained? And you can see from these diagrams of key metrics, volume fraction, surface area, tortuosity factor or relative diffusivity, triple phase boundary for the sake of quantifying it, they're very similar indeed. And in fact, we've had new training methods now since then, because the machine learning community is moving very quickly, that have enabled us to explore the variability between samples to increase that variable range even more. Understand microstructural data is the 2-point correlation function. And again, comparing our data set to our generated samples, we find that they are extremely similar indeed. So that's, to some extent, a solved problem. What can we do with this that's actually useful? So here are a few examples. One of the things we can do is force our generated data to have periodic microstructure. Okay, so if a particle comes off on the right-hand side of the volume, that same particle re-emerges on the left-hand side of the volume. Same with top and bottom and left and right, front and back. Okay, why is that helpful? If you would like to simulate a volume of battery structure, these microstructures are hierarchical. Things happen at a range of length scales. And as has already been alluded to at several points this week, you can't simulate at your full length scale of interest with your finest resolution of interest at the same time. Your computer would set on fire. So how do you get around this? Well, one of the approaches that's been used in the CFD field for a very long time is applying periodic boundary conditions, and that can make a control volume feel larger than it really is to the emergent behaviors happening within that structure. But that's not possible in a tomographic data set, because the data itself, the microstructure itself, is not periodic in any meaningful sense. So we can force it to be periodic, and that allows us to impose periodic physics at the boundary conditions, and that allows the microstructure to be more representative for a smaller volume, and therefore will increase or reduce the cost of your simulations. So to give a visual example of that, here's just a 2D slice, and I'm simulating diffusive flow through the black phase from top to bottom. And the bright sort of orangey red bits show regions where the flux density is high, where it's moving faster, as it were. And that's with mirror boundaries imposed on the left and right-hand side of the microstructure. If I now, or even though this microstructure itself was periodic, I've forced it to be a mirror boundary, because mirror boundary is what we use in almost all microstructure simulations, because we have no choice. However, because this microstructure is periodic, I can turn on periodic physics as well. And now you see quite a different distribution of flux density across this microstructure. So if I highlight a couple of key areas to you with these little yellow circles, these are in the same area, right? Clearly, there's a much higher flux density in this one because the flow has been able to come off one side and re-emerge back onto the other. And again, up here, a region in the mirror boundaries, which was totally unused in the periodic system, is now being made use of. So the thing to bear in mind is when you impose these mirror boundary conditions, as we intuitively know, there are paths that go off the side of your volume that appear to be dead ends because you're just using a subvolume, but you know intuitively that they are not dead ends. Had you had a larger volume, they would have carried on and reconnected with the rest of the network. So your mirror boundaries was the best you could do with aperiodic microstructure or with random microstructure. But once you can force it to be periodic, you can take advantage of that. And what you find is that it has a significant impact on some of the metrics that are relevant to batteries that you might extract. And tortuosity factor, or relative diffusivity, is a very good example of that. So here is a nice image that shows I've just stamped the mirror boundary response 1, 2, 3, 4 times. Okay. Now, if I once again impose the periodic boundaries instead, and I've stamped it 4 times, you can see, just to highlight again, just how different the response is when the physics is allowed to wash off the sides of the image. Okay. If you would like some very large volumes for your simulations, if you're planning to do some simulations and only have a small amount of data, tomographic data or in silico generated synthetic data, and you would like a very large data set to try and make your volume representative for your simulations, get in touch. We can sort you out with some. Okay. And when I say very large, I suspect you can't see this animation, but I do mean very large. Once you have our machine, our generator, you feed it actually an input. And when you're training it, you feed it with some Gaussian noise in a vector form. So maybe you feed it a 100-dimensional vector. You now have what we refer to as a latent space that you can move around. And at different points in this latent space, you observe different types of microstructure. And therefore, we are currently looking at optimizing the battery performance by moving through this latent space, but staying constrained within battery microstructures that are realistic compared to our training data. And so that's the process that we're currently involved in within the group, and it's very exciting, and we're looking to collaborate with Alejandro on that and try and force the realism of his manufacturing simulations into the navigability latent space optimization of our generator. So that's very exciting indeed. A key concern, a key frustration with these processes is that you are now dealing with all of these very high dimensional, unintuitive spaces, parameters that don't necessarily mean anything obvious to you. And I really like this piece of advice from Geoffrey Hinton, who's one of the godfathers of machine learning, to deal with hyperplanes in 14-dimensional space, visualize a 3D space, and then say 14 to yourself very loudly. And then you get the picture. I think this works very well. Okay. There is a warning for myself and for all of us, which is that if you start trying to do optimizations based on simulations, you can end up with silly results. And the results will be absolutely correct if you've got the maths right, based on the simplifications that you've made in your electrochemical model. So, a good example would be that in many battery models, we ignore electrons. We just assume that they can get wherever they need to be. But if you tell your optimizer to use the results of a simulation to optimize the microstructure, but you've said that electrons don't matter, then it will, of course, remove all of the CBD, because it probably doesn't have gravity in your simulation, so the particles will stay where they are. And it also doesn't need the CBD to get the electrons where they need to be if you have told it that they aren't a problem. So always your optimization will only optimize the actual model you've given it and not the reality that you were expecting underneath. So be wary of this. Right. The next section is just a quick introduction before moving to the second paper. And it's just a refresher for some of you about tortuosity factors. Some of you may have measured them. Some of you may have used them in models. There are three sort of metrics that I'd like to talk about. The first two are quite distinct and often muddled in the literature. One is the geometric tortuosity factor, which is a measure of path length difference. And I've used zeta to denote it here. And you can see in the figure I've got that there's some kind of wiggly red path moving through an obstacle-filled domain. And it's the relationship between the path wiggling through to the actual displacement distance in total. The trouble is this is very badly defined in most 3D geometries. Where should it have started? Where should it have finished? How wide a berth should it have given the obstacles? Not a well-defined metric in porous media. The more conventional tortuosity factor for microstructure is the diffusive tortuosity factor. Okay, and this is the ratio between the sort of measured transport parameter and the intrinsic transport parameter of the transporting phase. Okay, and so I've shown you a sort of a concentration gradient of some red diffusing species going through that material there. And this one is what we mostly use, or a parameter, an effective parameter derived from it, if you are looking to parameterize a Doyle-Fuller-Newman type model, a P2D type model. But I'm going to talk about why that may not be the right choice. And that's what the next paper is all about. And to add more confusion to the mix, there are some scenarios where those first two definitions are related, are mathematically related, and that is only for what we refer to as capillary pores. So systems where the cross-sectional area of the pore normal to the mean direction of flow is constant, so a nice capillary path. And in that case, they are related to each other. But that's basically not relevant to any real microstructure system that we see. So this relationship and tau squared and all of this should probably be ignored. Tortuosity factors. Here's the intuition, right? And you'll need this to process the next part of the work. Here are three structures. Each structure, the conductive phase, the phase of interest, the transport phase, is the white phase. And I am applying some kind of potential difference, a concentration difference, a voltage difference between top and bottom. And I would like the flow to get through whatever type of flow it is. Okay. The first structure has a tortuosity factor of 1 because the path is direct from top to bottom. The second structure has a tortuosity factor of about 6 because not only is the path about 3 times as wiggly, but it's about half as wide. Okay, so it's not just about path length, but it's also about path constriction. And the last tortuosity factor underneath the standard definition is actually infinity. There is transport phase material there, material that can do the transport you're interested in, but it's isolated. And therefore, based on the conventional definition, that would have a tortuosity factor of infinity. That's the basics. But here's part of the problem. These three structures all have a porosity, so a volume fraction of the transporting phase of 50%, but they also all have the same tortuosity factor. Okay. And so here's some kind of scalar field from a simulation, and then here is the flux map for each of them. And what you might see already is that although they have the same volume fraction and the same tortuosity factor, which is pretty much all of the metrics that you would use to characterize microstructural complexity in a conventional 1D battery model, they would clearly have very different behavior. Okay, and that theme of non-uniqueness, that theme of very widely varying behaviors from the same microstructural homogenized parameters is what we're going to explore. So here is a follow-up to that piece of work that then kept the sort of diffusion equation as its basis, but transformed it into the frequency domain. Okay, and so that's what the system of equations looks like now. And here's a nice example where here are 7 microstructures, just getting overexcited now, 7 microstructures that all have the same steady state result. So they all have the same tortuosity factor. They all have the same volume fraction. But these in this Nyquist plot are diffusion impedance spectra, calculated diffusion impedance spectra for these simple 2D microstructures. And as you can see, they are very different from each other. The black line that doesn't have markers is the finite length Warburg analytical solution. The rest are all responses from the microstructures that we see. So I think it's important to keep in mind that already, no matter how nicely you calculate your tortuosity factor, no matter how brilliant your tomography data is, you shouldn't be surprised if your one-dimensional model does not agree with your actually measured battery impedance data, because it really is a 3D structure. 3D microstructure will have different performance than 1D than this kind of homogenized system in many cases. So here's the next paper with Tointu and Arnaud and Benoit and Bruno and Charles, and the paper is supposed to be deliberately a bit provocative, right? The electrode tortuosity factor, why the conventional tortuosity factor is not well suited to quantifying transport in lithium-ion battery electrodes, and what to use instead. So there are well-defined and well-used methods for measuring tortuosities of things. And here's the sort of simplest way of thinking about it. I've got two lithium metal foils, and I can put some, porous medium between the two. Let's say some a separator material, and I flood the whole thing with a lithium salt in solution. Okay, there's a time domain approach where I apply a steady state current. So I get a current, and that will build up gradually a concentration profile across my material. And then I stop that current, and I observe with two reference electrodes this concentration gradient relaxing, and I measure that potential relative to the two foils, and that allows me to understand how difficult or how obstructed the transport was through that porous medium compared to if I just had the liquid. There's also a frequency domain approach where I can take my high frequency response from the impedance spectroscopy and understand that that's a migration-driven process going backwards and forwards through the microstructure. That has problems when you want to characterize electronically conducting materials, which is the case for battery electrodes. So two slightly modified takes on that have been developed for battery electrode microstructure. One is the first time domain approach again, but you've now got your freestanding electrode is in the middle, okay, the orange region, but you have to put, because it conducts electrons, you have to put a separator on either side so it doesn't just have a short circuit of the electronic current through the system, okay? And you have to actually have a model of this because the electronically conducting solid of the electrode can also see the potential field and will distort it. And there's also an equivalent for the frequency domain approach. And this is where you have two electrodes, conventional porous electrodes on foils, okay? Put a separator between them just to make sure they don't touch each other and have an electronic short circuit. And you do impedance spectroscopy, but crucially, you use a non-intercalating salt. So you're not actually letting, for example, the lithium go in and out of the solid phase. It just accumulates on the double layer of one side and then relaxes, or of each side and then relaxes again. Okay, so these are the two analogies we have to that simplified method I showed on the previous slide. So the conventional tortuosity factor that I introduced 2 slides ago is a bit like the restricted diffusion approach here, where you just see things flowing through in one side and out the other, flowing through a porous medium. I want to talk about the fact that we believe that this symmetrical cell method, the ESCM, is actually measuring a different parameter and one that is much more relevant to battery performance than the conventional tortuosity factor. So let's go to some nice basic microstructures again. These 4 microstructures have been drawn in Microsoft Paint, my favorite microstructure generation program. And they are all based around microstructure A. So you can see I've taken Two has taken microstructure A and then added sort of fronds or blobs to it. Crucially, B, C, and D all have the same volume fraction of the black phase, okay, which is a little bit more than microstructure A. And each of them have got different interfacial areas. And this is the first time I've mentioned interfacial area today. But of course, in a battery, what you're really trying to do is get out of the interface on one electrode, across to the other side of the battery of the cell and into the interface at the other electrode. You aren't trying to flow all the way through an electrode and out the current collector. That isn't what you're trying to achieve. So why do we use a tortuosity metric that models that exact behavior? Okay. Using our approach, or using the conventional tortuosity factor, sorry, these microstructures have been designed so that they all have, or B, C, and D all have the same tortuosity factor, but actually A, B, C, and D all have the same McMullen number, which is this ratio of tortuosity factor to volume fraction, okay? And McMullen number is just directly how impacted was the transport by your microstructural configuration, okay? So they've all got the same McMullen number. But they'd clearly be very different if you wanted to use these types of macrostructure for a battery. So that's problematic. If you use this frequency domain response, where you're trying to get in and out of pores at either side of a symmetrical cell, they now have quite different numbers. And clearly some are much better suited to being a battery than others. And I'll come back to which ones we believe that is in a 3D representation of that. But again, our numerical approach, which is what Tu and I developed together, the numerical approach gives you a full impedance spectra of this behavior. Okay, so here's something that looks a bit more like a battery. Okay, it's a symmetrical cell. What have we got? Here, if you can see my laser pointer, where the little blue box is at the top of the microstructure, we've got a very particular designed microstructure. Most of the microstructure has got a volume fraction of 35% porosity. But a thin layer at the top, I think it's 10% of the top, or maybe 20%, has got a reduced porosity. So it's denser. It's now only got 20% porosity. Okay. Crucially, the conventional tortuosity factor doesn't know whether you're going from top to bottom or from bottom to top with transport. It is agnostic to this. Okay. It can do measurements in different of the 3 Cartesian directions, but it cannot differentiate between the positive x direction and the negative x direction. So this microstructure, which has a dense layer, is the location of that dense layer at the top or the bottom cannot be measured with the conventional tortuosity factor. But it can be measured with our new metric, this electrode tortuosity factor that we are proposing or have proposed. And you can see, if you now look on the left-hand side of the 2 Nyquist plots, when that dense layer, i.e. when the low porosity region is sandwiched either side of the current collector, of either side of the separator, so right in the middle of the cell, the total transport resistance experience is much higher. Okay, that battery is now facing severe transport losses in the electrolyte phase because you've blocked off all the pores right next to the separator. And conversely, when you turn it around and put the dense layer next to the 2 current collectors, you now have a much reduced impedance from that transport process. Okay, and this is exactly in line with our expectations. And this is a real effect that you see in real electrode manufacturing processes, where you can have, for example, non-ideal drying rates from your electrode, and you can end up with a skin, almost like custard skin, settling on top of your electrode and forming a low porosity layer on the top that doesn't allow trivial transport of your lithium ions through the pore network. So this is really important to be able to differentiate this. And just to reinforce that point, no conventional battery models have the ability to capture this in the standard 35 parameter set of the Doyle-Fuller-Newman paradigm. So the conventional tortuosity factor is about flowing through a medium, in one side, out the other. It's a finite length type concept, okay? Our new electrode tortuosity factor, which is just as cheap to calculate, okay, I'm just changing the boundary conditions a bit, is about transport from one surface, i.e. next to the separator, into the material through the pores in a migration fashion and into the interfaces of the active material. Okay, which is very much more aligned with how a battery's performance would be determined. And so we think this should be the go-to metric for taking image-based data and using that image-based data to try and parameterize a battery model instead of the conventional tortuosity factor. It has some slightly uncomfortable features. One of those features is that it can have a value less than 1. So in the conventional tortuosity factor, the minimum value of tortuosity factor is 1. That's a direct path from the top to the bottom, as it were. Our system, if you think about a transmission line model or a columnar pore going directly through a microstructure, that is tau or tau E, the electrode tortuosity factor. That is tau E equals 1. What it's like to come in one side and access all of those bits of surface area. And you can imagine a series of resistors, each one with a little capacitor at that surface. Okay, that's tau equals 1. But depending on your distribution of surface area as a function of depth and the widths of your flow paths as a function of depth, you can do better than a straight pore. And I think we would like to believe that this is something actually quite fundamental to the battery community. We know that some of these metrics, like surface area, you can say, well, in principle, the more surface area, the better. Of course, there are reality constraints like SEI growth and manufacturing problems. But with the tortuosity factor, the conventional tortuosity factor, it seemed as though the best case scenario was straight pores, even though some of you who have thought about it some more may have thought, maybe that's actually not the best, right? These concept of graded structures where you can have, you know, more surface area near the top and denser regions near the bottom seemed intuitively correct, but we didn't have a metric to try and extract that structural property. Well, now we do, and it's called the electrode tortuosity factor. So if any of you would like to know more about it, we've got a paper coming up very soon. It's just been accepted into NPJ computational materials, so hopefully it'll be coming up fairly soon. And perhaps, you know, more importantly or complementarily, we've integrated it into a software package, so you can calculate this thing and you can just download it from various places, GitHub and MathWorks and various places. So there's a new version of some software I created a while ago, and that'll be coming out, and it'll have this new electrode tortuosity factor solver built into it. And you can compare the two, calculate the conventional, calculate the new one, and see whether that aligns with your understanding of how these simulations should describe your microstructure. So with that, Alejandro, that's all the things I wanted to say today. I'd like to thank my sort of microstructural team, Andrea, Liam, Steve, and Charlie, who do fantastic work. And also, again, to thank my collaborators in Picardy for this absolutely brilliant collaboration. It's been really painstaking because we've debated so much between us about exactly what things this metric is describing, but I think we now have a real consensus about this being the way to go for the battery community. And of course, my extended team at Imperial, the Electrochemical Science and Engineering Group. So thank you very much for the invite again, and I'd be happy to take your questions.
Thank you very much, Sam, for this amazing presentation with amazing results as usual. Thank you very much again. So it was very glad to hear you, to listen you talk. So you have many questions waiting for you in the question session. So I think you can.
Okay. Yeah. Wow. Blimey. Right. So from Matteo, how to use this electrode tortuosity factor in a DFN?
Sam, you can click in the start live answer, and then okay, yes, and then you will answer it.
Great. Very cool system. How to use this electrode tortuosity factor in a DFN? Drop it in, right? I.e., if you've got a space for an effective transport parameter, then the effective one is the intrinsic multiplied by the volume fraction divided by the tortuosity factor. Our suggestion is it's a 1-for-1 substitution. Take out the old tortuosity factor and replace it with the new one. Is it just for characterization or can it be used in the equations? Yeah, it just goes straight in. Okay. Have you heard about the concept of constrictivity, which is a sort of bottleneck property? Oh, it is. I see. I'll follow your rules, Alejandro, sorry. Have you heard of the concept of constrictivity, which is a sort of bottleneck? I have, and my feeling with it is a bit like the geometric tortuosity factor, which is a path length only. Constrictivity is constrictivity only. But the reality is you want some kind of PDE solver that takes account of both path length and constrictivity. And the reason, one way to think about that is resistance is rho L over A, right? So each point in space can be thought of as a little resistor. So it's about both path length and path constriction that defines the total amount of transport resistance that you'll see. And not just that, but the coincidence of those two properties. A long, narrow path that's wiggly or a short, straight path. These are very different things. So constrictivity is also limited in its use. You have to consider all these things at once. Okay. thanks for your talk. In terms of the time of intercalation, how is this new tortuosity factor impact the time of intercalation, and what will be your recommended in terms of electrode microstructure to achieve better times? So, of course, we don't intercalate. We just get to the surface and charge. Okay, so we are just looking at transport through the pore phase. We are ignoring the solid phase because eventually you just have to recreate the DFN model. And if you turn on your DFN model and don't allow your interfaces to intercalate, you'll recover our result, our tortuosity factor, which I think is a good clue as to the utility of it, as in analytically. So what we can tell you is in scenarios where perhaps you've got a very thick electrode and therefore you're struggling to get lithium all the way down from one side to the other, our tortuosity factor would hopefully give you the more realistic metric to characterize that in that resistance to transport. Okay. Yvonne, what the preparation method used to make the electrode samples have a homogeneous tortuosity factor evenly? I think this is very challenging. Agreed. And you know, our paper is a simulation paper. A homogeneous tortuosity factor, you don't forget you can integrate over the area of the cell. So your homogenization occurs across the width very easily, but your homogenization in the through plane direction, much more tricky. And is a uniform tortuosity factor even the target anyway, right? Maybe you want to have very high surface area, dense small paths at the bottom, and maybe you want to have some nice super highways for transport near the top, right? It's not trivial still what the ideal microstructure looks like, but I think this metric will allow us to explore the optimization space in a much more instructive way. From Jayachandra, how do you treat the stochastic nature of your microstructure while homogenizing? Well, we generate large enough volumes that it homogenizes. I think is the simple answer. We are currently writing a paper that uses our generators. So having broken free of tomography by learning the essence of the microstructure, we can now generate arbitrarily large microstructures with consistent properties. This allows us to do a representativity study in a way that is impossible with just tomography data, because you'll never have more data to prove that the previous set was already representative. So that will be coming out very soon. Okay, continuing to explore. Okay, from Mark. Thank you, Mark, for setting us up with all the tech. It's been fantastic. Thank you for the great speech. How do you validate the hyperparameters of D and G, i.e. the number of layers, types of convolutional layers, activation functions? Do you do this empirically? It's a fantastic question. It's a notoriously tricky question in machine learning. We have had some breakthroughs, to be honest, in the past couple of months around this space, and certain configurations which are taken as okay, but not necessarily extremely well suited to a homogeneous microstructure. So we have had some breakthroughs around information uniformity in the system, and we'll be publishing those very soon as well. It is not totally well defined. I don't think it's unique, but it's also not totally arbitrary. Can electrode tortuosity factor be calculated in cylindrical coordinates? Two answers to this. One, yes, right? And I've done this, or I've done the equivalent thing for a cylindrical microtubular fuel cell. But two, I wouldn't bother. The battery electrode, I would argue, is not cylindrical on the length scale of the electrode. As far as the electrode's concerned, in my view, it thinks it's flat, because the radius of curvature compared to the thickness of the electrode would allow you to assume that it doesn't know it's a cylindrical cell. It may as well be a pouch cell as far as it's concerned. In my view, I'd be happy to be corrected on that, but that's the assumption I'm working on. But if it was needed to be done, it absolutely could be done, but I wouldn't code it up unless someone could really convince me. Okay. Question here from Simon. How do you calculate the electrode tortuosity factor based on the symmetrical impedance signal? You as ever are, essentially V equals IR, right? So you're as ever, you're extracting your impedance by taking a ratio of your current and your voltage, right? And you'll end up with an impedance spectrum. And that, in fact, I can show you more convincingly than that. Okay, these ones, right? Notice these microstructures, or these Nyquist plots, don't quite go to the origin. There's a small offset. That small offset is about transport through the separator. We've actually put a microstructure either side of a small separator region in the simulations. Okay, so we first remove that, and then we are taking the width of the region from the axis intercept to the asymptote as our as the metric that we can use. And the equations that justify that are built into the paper, but you're basically comparing it to a conventional what is effectively finite space Wahlberg, although actually mathematically it's not, because you're looking at the surfaces. But yeah, all the details in the paper, it's quite a lot to do by voice. And this is to generate the impedance spectra, but we're working on a solver now, which should come out fairly soon, which just does it in one shot. Okay. From Jan, to have good LIB performances, how should the porosity or diffusive tortuosity factor, which commercial materials are close to that? I don't know. In fact, you'd be better off asking Alejandro than me. I think, which the best materials, I honestly couldn't tell you, but I'd be happy to characterize any materials that you did have to try and establish the relationship that is actually there. Thank you for your talk. Is it possible for the tortuosity factor to be less than 1? So conventional tortuosity factor, no, it's defined between 1 and infinity. The tortuosity factor for electrodes, the electrode tortuosity factor, can be from 0 to infinity in principle, i.e. it's thinking about how does your system compare to a straight pipe if you wanted to get into the walls of the pipe and not out the other end of the pipe. And of course, you can do much better than a straight pipe for that. Okay. How many SEM images you need to create a useful training set? Good question. There's no straightforward answer, because also there are complicated questions around resolution, as always. So depending on the size of your features relative to the size of your domain, relative to the scale of your anisotropies and heterogeneities. So we can work with, we've been doing this for flow battery data, fuel cell data, all kinds of interesting data sets. And we found that different amounts of data are required for different systems. But a usual tomography data set, sort of 500 by 500 by 500 voxels will be the nice bit in the middle. That's loads of data already, as far as we're concerned. Okay, Alejandro, can you see any more? Have I missed anyone?
You have a question from Emiliano Primo. If you go to the chat.
Okay. Oh, there are a few more at the top as well. Emiliano. Sorry if you spoke about this in your presentation, but I didn't follow all because I was answering questions. Thank you, Emiliano. What about the kinetics of formation of double layer, the impacts the impedance spectra? Also, regarding the effect of the electrode thickness, do you think any impact on the tortuosity? So, good questions. So our double layer is just a capacitor, right? So we are just, it's very simplified model, and that's a speed issue. We are just wanting to keep it a simple model to try and extract this as a singular parameter that looks like this transmission line. Electrode thickness. Well, again, so your scaling of your pore feature size relative to your electrode thickness and how your straight pipe pores would compare to the available surface area perhaps near the separator, these things will all scale. It is fundamentally a non-dimensional parameter, but I suspect as your electrode gets thicker, of course, the impact of your tortuosity factor will be more pronounced because you're having a hard time going through a longer volume. Okay, a few more up here. So from Anando, do you also have or plan to take into account the relative channel stiffness and varicosity? Well, I wasn't planning to. If you could, you're very welcome to drop me an email and explain how I might and whether I should. I'd be delighted, but certainly it wasn't in my plans for now. Have you performed modeling validation for various electrode thicknesses and Candring forces applied? If you have, you checked if the tortuosity factor is constant during cell cycling at various applied current? I mean, those are two fantastic questions. The answer is no, But Tu and Charles and also Alejandro and his team, these are things that they are working on, trying to characterize these microstructures at different calendaring, as you've seen over the course of this week. And I think, you know, this stuff is, we're in the moment now in the battery history where this stuff is going to happen, and we're going to get these relationships established and finally allow us to optimize batteries. Because of course, don't forget, there is no one particular good battery microstructure. It should be paired to what you actually plan to do with the cell. If you want an energy cell or a power cell, whatever. Okay, and is it constant? Brilliant question again. I don't know. The imaging is, of course, very difficult to do in operando at different states of it, you know, especially, for example, with a silicon anode, where you know these materials are hugely changing in size and morphology during different stages of lithiation. I'm sure these transport properties would be radically different at different stages. So I think it's a fantastic question. If anyone's got any data that could show it, I would love to see it. Given the heterogeneity of the microstructure, the periodic boundary conditions might be very huge in number. I'm not quite sure I understand that one. The point really just being that we can generate a structure that looks like the real stuff, but we can also trick it into thinking it's in like a spherical universe, if you want, where what comes off one side goes in the other. So for a given size, our microstructure will look a bit more representative than a non-periodic structure of the same size. So it just means your computations become a bit more efficient. Currently, you'll all have seen that, you know, on the edges of your boundaries, you might have just seen the edge of a particle, right? You know, in reality, that particle comes off over here on the side. But all you can see at the edge of your boundary is a little sliver, a little tiny thin slice. When your simulation has a mirror boundary, it thinks that thin slice is part of a thin section. It thinks you've got one really weird shaped particles. In fact, currently all 3D battery simulations on their boundaries think that all the particles are crazy shapes. They'll think there'll be weird shapes like this. They'll think there'll be weird peanut shapes. Anything that has been chopped off at the side, it reflects onto the other side with a mirror boundary. And that is our motivation for this periodic structure, that now you get real structures all over. In fact, with a periodic system, there is no boundary. It cannot tell the difference.
Thank you, Sam. So